Hello, this is the first coding video. So we're going to be working with um, Python and NetworkX and Gurobi. So first you'll need to log into Canvas and scroll down to this Python Gurobi module. Click on the example Python NetworkX/Gurobi codes link. Open up this web link. And this contains a whole bunch of codes that we're going to write. These are all of the ones that I guess these are completed codes. And then inside of this starters folder are the ones that we're going to be doing the videos. Okay, so if you've worked with GitHub before, you're welcome to clone this repository on your PC. But if you haven't used GitHub, maybe the easiest way to get started is just to download this code as a zip file. So I'll click on the green code box, then download zip. So that'll download the zip file. I'll need to unzip it. And for simplicity, I'll just keep it in my downloads folder. But in your case, you may want to put this in a separate folder wherever you want to store it on your computer. And we'll click on starters. Okay, so this NetworkX Basics, this is the one we're going to run. So I'm going to use Jupyter Notebook. So I'll open that up. Okay, and then I'll just have to download or navigate to my downloads. Then I'll have to find this folder that I just unzipped. Okay, so here's the one that's unzipped. I'll go to starters. Okay, so we're going to start with basics. Okay, so this is the graph that we're working with. So you may recall this from the shortest paths lecture. Okay, so we're going to represent this graph in NetworkX. So first, what we'll need to do is import NetworkX, and I'm going to import it as NX. And if you've got, I think, a standard Anaconda installation of Python, you should, I think, have NetworkX pre-installed. Okay. So I've imported NetworkX, and now I can create a graph object, and I'm going to call it D for directed graph. So I'll need to do nx.digraph for directed graph. Okay. So at this point, this graph has no nodes and no edges. So if I print d.nodes, I just get an empty list. And if I print d.edges, I just get an empty list. Okay. So first, we're going to add the nodes. And so I'll create this list called my nodes. And if you look in this graph, it looks like the nodes are numbered 1, 2, 3, 4, 5, 6, 7, 8. So I could just type that out. Okay, so then I could add these nodes to my graph. So I'll do d.add nodes from. And then the argument here is going to be this list of nodes. And then now if I print d.nodes, let's say 1 through 8. Okay. So this is one way to add these nodes to our graph. Another way, maybe for now, I'll just comment this out. So reinstantiate that graph as the empty graph. So now there are no nodes. So I could add these in one line. So I could just do d.add nodes from, And then here I can just use this range function in Python. So I want the range going from 1 through 8. And the way that Python works, I actually need to put in 9 because it'll return the range of all integers going from 1 up to, but not including this number. Okay, so if I did that, and then I printed b.nodes, and again, get 1 through 8. Okay, so that would add it in one line. Another way is that I could add these nodes individually one by one. So to show that, let me get an empty graph again. Has no nodes. Okay. So now I could just say for I in range, and I could just say 9. Oh no, actually I think I should say 1 through 9 because Python will do 0-based indexing. Okay, so I want to make sure that I have nodes 1, 2, 3 all the way to 8, and not nodes 0, 1, 2, 3, and so on. Okay, so range 1 through 9, and then I can do d.add node, and then just the single node I. Now if I were to print d.nodes, it's again 1 through 8. Okay, so either of those, any of those 3 approaches would work, but I'll just go ahead and use this first one. So I'll just rerun these cells. Okay. So now I have a graph with those nodes, and if I were to print, maybe I should print it. If I were to print b.edges, I currently have no edges. Okay, so I need to add some edges, and going from this picture representation, I don't know of a better way to do this than just to type it all out. And also, we're going to want to add these edge attributes. So we have an edge going from node 1 to node 2, and its weight or distance or length is 8. And so I think it'll be convenient if I just go ahead and define the edge weights. This will be a Python dictionary that will map a node, ij, to its weight. Okay. So the first edge that I'll write is 1, 2, and its weight is 8. The next edge, let's say, is 1 to 3, and its weight is 15. The next edge is 1, 4, and its weight is 9. Then I'll just do these in lexicographic order. So 2, 3, its weight is 13. And this might get kind of long, so I'll go ahead and return here. After 2, 3, let's do 3, 5. So that's 4, 5 is 13. At 3, 7 before that. 3, 7 is weight 5. Okay, then after 4, 5 would be 5, 6. Whose weight is 7. Then 6, 8 is next lexicographically. That's weight 4. And then 7, 6. 9. 8. It's weight 8. Okay. So just to make sure that this is working properly, I'm going to go ahead and, after defining this Python dictionary, I'll go ahead and try to refer to something inside of it. So maybe I could refer to what's the weight of edge 1, 2. So I'll print that. It should be 8. Okay. So it appears this Python dictionary is working. Okay, so I'll want to add each of these edges, and I also want to add this weight attribute to that edge. So for each one of these edges, I could do this, yeah, for every edge ij in edge weights keys, the keys of this dictionary. I'll want to add edge. And since this is a directed graph, as I define up here, edges will be from this node to this node. And then if I want to add other attributes, I'll add them here. And so the weight, this is the one attribute I'm adding. And the weight of this edge ij is edge weights ij. So after adding all of those edges and also adding their edge weights, let's just check and see if it printed or if it worked properly. We'll print this. Okay, that appears to be the correct list of edges. And then also to double check, let's make sure that we captured the weights of those edges. So for edge in d dot edges, I'll print that edge I to j, and maybe I'll use parentheses here. Right there. As weight. Now I can refer to the weight in the graph. So this will be d dot edges ij and the weight attributes. Okay, so you might need to be a little careful here with stuff in here. Okay, so let's give that a go. Okay, so edge 1, 2 has weight 8, which I think that's what we had. Edge 1, 2 has weight 8. Okay, all of this looks pretty reasonable. Edge 7, 8 has weight 18. 7, 8 has 18. Okay. So this is one way that we could add the print the edges. We can also print them like this for every edge E in d dot edges. Print that. I'll print this. But here, I'll simplify this and I can just write E. And then over here, I'll also need to refer to E. Okay, and that looks, that's, I guess, easier to code, and it also looks nicer, I guess, because of the way that Python treats these strings. It always puts a space after each one of these things. I think I could have adjusted that, but it would have taken a little bit of extra code to avoid these extra spaces. But in any case, I think this is probably easier to code if you're printing something. But I think because of the way this add edge function is defined in NetworkX, it really is important that we have the individual, like the tail and head of these arcs. I think if you tried to add edge E here, you might get an error in NetworkX. Okay, so I think we have our graph, we have the nodes, and we also have the edges. And Fortunately, NetworkX has a lot of helpful functions, one of which we can use to draw the graph. So inx.draw, and then I'll just pass as argument the graph D. And so that's the drawing that NetworkX chose. So remember, a graph is just a collection of nodes and a collection of edges. It doesn't have like node positions. There's no embedding explicitly in the graph. So if I draw this multiple times, NetworkX may choose different drawings. But ultimately, it's the same kind of topological structure. It still has the same nodes and the same edges connecting them. Okay. We can also draw other pieces of information in this drawing. So one thing you might want is the labels on the nodes. So like node 1, node 2, and so on. So to do that, all I need to do here is to write with tables equals true. Okay. So again, the positioning of the nodes is different than in the original picture, but the graph itself is the same. It's just a different drawing of the same graph. Okay. Another piece of information that was in our original drawing that's not here was the weight of the edges. So we can also draw that. And this is a little more complicated to do. This is at least the best way I've found how to do it. So it's using this draw network tables. And okay, the first argument here is the graph. And then we have to specify the positions of the nodes, which this position dictionary I'll get in just a second. And then the edge labels that we're going to use are the edge weights in our dictionary from earlier. Okay. If we're to run this right now, you would get an error because we haven't defined this position dictionary. So that we can get from a few different NetworkX kind of embedding algorithms. So one of them is this spring layout. So we'll apply this spring layout function to our graph D, and then that will tell us what are the positions of these nodes. And then I think so far we might still get an error. Let's check if we try to do this. Okay. So I think we're getting just the edge labels. So we're not drawing the nodes or the edges between them. So for that, we need a separate inx.draw call. So we're going to draw the graph D. And we want to make sure that the positions of these edge labels matches the positions of the edges themselves. And so whenever we invoke inx.draw, we'll have to make sure that we're using the same node positions. And like before, we want to label the nodes. Labels will equal true. Run that, we get our graph. And maybe I'll run this a few times just to get a prettier drawing. Okay, this one doesn't look half bad. Okay. So next up, we will, because it would be helpful if we could import and export these graphs so that you don't have to type them up every time. So I've given you some helper functions here in the starter that will write this graph to a JSON file. And JSON, if you don't know, is a JavaScript object notation. Okay, so this function we can use to write this graph to this file. And then we also have a function that will read the graph from a JSON file. And so there we just have to pass as argument the file name. Okay. But first, let's go ahead and save our network, which is D. We'll save it to an external file using this write to JSON. And the first argument is our graph D, and then the next is the file name. So we get to choose file we want to save this under. And so I'm just going to call it my network JSON. I guess also before invoking this function, I need to define it. So I'll run that cell above it. So now we should have the ability to call this function. So I'll run it. It appears everything works properly. And for illustration purposes, I'll want to read this graph back into my code. And so right now, I'll just go ahead and clear this graph. So basically, I'll just call this digraph function again to create an empty graph. So it should have no nodes and no edges. So maybe let's check that d.nodes, and then I'll print d.edges. So this should be empty. In fact, yeah, no nodes, no edges. All right, so let's try to read in the file again. So read graph from JSON, and then I'll pass whatever file I want to read in, which is again file name. And this function is going to return this NetworkX directed graph. So I'll save it to D again, and then I'll print the nodes and the edges. So I read from the file, I have my nodes, and I have all these edges. And let's just double check also that the edges exist. So, or sorry, that the edge weights are still attributes of these edges. So for every edge in d.edges, I'll print that edge E has weight. And I think those are the same edge weights. I remember edge 1, 2 had weight 8, and that last edge had weight 18. So I think we're good.